everyone, welcome again to our AWM Grad Seminar. Our next speaker is Samantha Brozak. She is a PhD student from Arizona State University. Her talk today is on integrating wastewater surveillance with dynamic modeling to track and predict viral outbreaks. So Samantha, please go ahead.
All right, thank you. Let's see, let me go ahead and share my screen. All right, actually, let me do one more thing. I think I shared the wrong technical screen, or else it'll throw a fit. All right. So thank you for having me. Thank you for the introduction. As was said, I will be talking about integrating wastewater surveillance into dynamic modeling. And I'll be talking about it in the context of COVID-19, but of course, the beauty of this is that we can apply it to many other kinds of diseases. So here's a quick rundown of our table of contents. So we're going to do an introduction. I'm going to run through basic mathematical biology first, and how we tend to think about these kinds of problems, and then we'll get into some numerical results briefly. I seem to have lost something important. Now we're good. All right. So I work on a team that spans the country, and we have a couple of papers trying to look at COVID-19 and wastewater data and trying to integrate them and see what we can learn. So what I will mostly be talking about is the first and bottom papers, the simple SEIR model and the making waves paper. If you're interested in a very mathematical type of paper, you can read the second one about viral variants. But what I will be talking about today is very, very applied in nature. So I'm a fourth year applied math PhD candidate. I actually just got my candidacy in December, which was very exciting. I work with Yang Kwong here at ASU, and I mostly do epidemiology and ecology. I was a middle school teacher at one point, and I'm currently an R&D intern at Sandia National Labs in Albuquerque, New Mexico. So stepping back, why would we model something mathematically? Well, maybe we can learn something about it that we can't experimentally, and ideally we can make predictions. Why we model diseases is because we might not know the impact of mitigation strategies. For example, when vaccines were being first distributed, because of demand, some countries were considering just giving out the first dose of a 2-dose regimen and only giving out that first dose. That way they could cover as many people as possible. So we could model something like that in order to see if it'll actually be helpful. There are ethical concerns. We cannot experimentally look at some of our questions due to the ethics of it. For example, vaccinating certain people and not others. And what we can do is work synergistically with experimentalists to find and answer questions. There's also a sense of urgency. For example, early COVID in March 2020, we had no idea what we were dealing with, and we had to get some kind of information in order to make informed decisions. We're going to have a crash course in disease modeling. So I will be talking about SIR type models, and these models split the population into mutually exclusive compartments. So S is susceptible, I is infectious, and R is recovered. It is assumed that once you're infected, you can't get sick again, just due to the time scale. We're usually working on a very short time scale of a couple of months. So that is why susceptible and recovered are split up. We define incidence as the number of individuals infected per unit time in days. And so we're going to use the notation S of t, I of t, and R of t to denote the number of people in the indicated population at time t. The change in susceptibles is going to be denoted here by the time derivative, and we lose susceptible people because they get infected. So we have a minus the incidence. To define this mathematically, we're going to let n be the total population. So then C times n is going to be the number of contacts that an infectious person makes. So you're only contacting a portion of the population. S over n is the probability of contact with a susceptible person out of the total population. And so the number of contacts that an infectious person makes with susceptible people is going to be the product of these two quantities, denoting in C times S. If P is the probability of transmission, then we can actually estimate the number of susceptible people who are infected by a single infectious person per unit time as the probability of transmission times the number of contacts you have, essentially, or the number of effective contacts is one way to think about it. So what we will denote this as is the total number of people infected per unit time is going to be beta times S times I, which is going to be the probability of transmission times the number of infectious contacts you have times the total susceptible population, and we multiply that by the total infectious population. Now, there are other things that result in population changes. So, for example, running through this quickly, the change in susceptible people, here is the first equation, and that is births. We grow the susceptible population by people being born. Another example is immigration. We lose susceptible people because they may pass away naturally or they get infected. If they're infected, then they move to the infectious compartment, and infected people can either recover or die of natural causes or die of disease-induced mortality. The recovered people will move to the recovered compartment. And it's this sort of framework of transitioning between compartments or losing or gaining in the compartments that really drives this methodology here. We're working with a really simple system of equations. I want to clarify that this is going to be the simplest possible model. And there's a lot that goes into that. This version of the model is an SIR type model. Because we're ignoring demographics, it's called an epidemic model because it's a very short time period where births and natural deaths don't really matter. The population doesn't change enough for us to account for it. The infectious duration is given by 1 over gamma days. So you can see in the dIdt equation here on the right, we have infected people coming in, and then we lose them in the term gamma I. And so it works out to be an exponential distribution where the average time of infection is going to be 1 over gamma days. The reproduction number is a very important quantity that we look at, and this is given by R naught, which is beta over gamma. And mathematically, this translates to the number of secondary infections generated by one infectious person. So if I am sick and I go into a totally susceptible population and I get 4 people sick, then the reproduction number is 4, which is tremendously high and very bad. But that is how we interpret this. There are problems with the SIR model. So it inherently assumes that people who come in contact with an infectious person are immediately sick. That's not what happens. There's usually a couple of days where you are not sick or contagious to other people yet. But we can fix this. We can add another stage to the model. That's fine. Instead of SI, we might have SEI, just to have a bit of a time delay there. The other problem is that not everyone has the same number of contacts with people. And these models really just have us working with averages, which is sometimes fine, it's sometimes not. There were super spreading events during the initial COVID epidemic for that first part, and the averages are fine until somebody is significantly outside of the average. There's also an interesting part here with statistical versus mechanistic models. So some people take different approaches to this. One thing I've noticed is that people like to think that whatever method they like is going to be the best method all the time. And I'm trained with ODEs, but there are lots of different ways that people have looked at these equations. Or looked at disease dynamics. Some people use machine learning models. Some people have used statistical models. In my opinion, for this specific application, the mechanistic models that we're looking at of the SIR type are appropriate because we actually have the underlying mechanisms of disease transmission, somebody coming in contact with another person. Depending on the statistical or machine learning model, they might just see a spreadsheet of numbers and, fit a curve to that, which is fine sometimes, but we're really leaning towards mechanisms so we can understand what's happening with the disease specifically. And this leads us to the often cited quote that all models are wrong, but some are useful. So we have some complexity trade-offs. Simple models will try to distill dynamics to make things manageable, to make things mathematically tractable, which is great. Hyper-realistic models may require information that we just don't have access to, which is even with the simple model we'll be talking about here in a couple slides, we still had problems trying to access certain information. What we're looking for really is the Goldilocks model, which is something that's good enough without getting too complicated and asking for too much information that we just don't have. So we're going to talk about wastewater data. The way this works, if you're not familiar, is that people in a community may be infected and then they transmit to each other. And for example, with COVID-19, people may shed virus through their nose, throat, and also in their stool. And the stool goes into the wastewater. And what we can actually do is track how much virus is in the wastewater and make forecasts, make predictions, try to understand what happened in previous waves, and really leverage this information. Now, a big question is like, okay, we have clinical data. The clinical data for COVID is amazing compared to a lot of other diseases. You will not find daily data for really any other disease, right? However, with clinical data, as we saw, it's quite unreliable. There's testing delays. People might not take a test because they don't know that they're sick. People might think it's a cold when it's COVID. People might not use the test properly, and then they get a false negative. So there's so many problems. And mortality data is better, but there are still reporting lags, how we classify a death as COVID-induced versus not. There's a lot there that's still going on. So we're going to use wastewater data. And with wastewater data, the benefit is that it's real time. We can get estimates for how much virus is in the sewers almost instantly. It's not invasive. We're not relying on, a chain of reporting here. And so it seems like a really great candidate for us to do epidemiological community monitoring. But there are challenges. I talked about how people shed virus into the sewers through their stool. We need to understand how people shed virus. It's time dependent. People who are in their early stages of being sick shed more virus than people who were sick a week ago. And it also depends on the person. Additionally, people who are sick but not showing symptoms, people who are sick and showing symptoms and contagious, and people who are recovered, they all shed viral RNA, which is what goes into the sewers. They all shed it at different rates. They all shed it for a different amount of time. So recovered individuals can actually shed viral RNA for COVID for several months after, and that can confound the wastewater signal. And it's very hard, if not impossible, to estimate the pre-symptomatic shedding in people who just might not know that they have it. The additional kind of wrench here is vaccine coverage and efficacy just also will really impact viral shedding rates as well as the variants. Some additional challenges come from the travel time in the sewers. So viral RNA, it goes from maybe a neighborhood over to the sewage plant. The amount of time it spends in the sewers, it will degrade the viral RNA, and so not all of the RNA makes it from somebody's home to the sewer or to the sewage plant. The temperature affects how much viral RNA makes it to the sewage plant. The flow rate in the sewers changes depending on the weather, and as I have recently found out, there are differences in experimental protocols, which means that cross-referencing some of this wastewater or like combining it, consolidating, is hard. However, these are challenges that we can try to meet. This is where that idea of hyperrealism versus something simple, we try to find that balance. And we did pretty good job, if I say so myself. What we're going to do is connect a wastewater-based epidemiology framework to a simple epidemic model. And we're going to use this tool to estimate the number of cases of COVID in a community at any given time. So our data comes from the Deer Island treatment plant in Massachusetts from October 2020 to January 2021. You'll notice this is very early in the pandemic, and so vaccines were not a thing quite yet. We also had information on RNA quantified at the plant. We had information on the flow rates and millions of gallons per day, temperature in the sewers. We had estimates for the travel time, but the people at the Deer Island treatment plant couldn't actually give us something really good because it depends on where you are. And so what we're able to do is, given some of this data, in particular temperature, because it's known to affect viral degradation, we can actually estimate the temperature-dependent half-life in order to get a first-order decay rate. And then assuming that the RNA decays exponentially in the sewer shed, we can estimate for a given temperature how much RNA actually makes it to the sampling site at the treatment plant. Now we also need to think about viral shedding. So this is from Wolfel et al. And looking at days post-infection, here we're splitting up our population into S, E, I, R compartments. So we have susceptible as S. E is going to be that exposed but not quite contagious class. I is the infectious class, and R is the recovered class. So what you'll see here initially is that in the first 3 days after getting infected, the viral shedding increases significantly. And then individuals who are sick in this red region here in the middle, denoted with an I, they shed quite a lot of virus, and then it slows down as they're in the recovery phase. And so naturally, you'll see here that a lot of these data points here in panel B that we tried to fit this viral shedding curve to, they come a bit later in infection, but that's because it was the best we had at the time. So what we will do is use this viral shedding curve and use this to kind of back solve how much virus is in the sewers and get that to the number of people who are infected at any given time. And what we will assume here is that people who are infectious or in the I class, those are the only people who are shedding virus. And this was an appropriate assumption for the time frame we were looking at, but it is no longer an appropriate assumption if you were trying to do this in 2024. So here's our model formulation. We add an exposed class for those who are infected but not yet transmitting. That's given here by E. There's a latent period of 3 days before somebody who's infected shows symptoms. We assume people are infected for about 8 days. And what we need to do is estimate the contact rate from the data. That is given by the parameter beta here in the first and second equations. To connect the data to the model, we include fecal viral shedding by individuals. So we only add one more equation, which is great. The dynamics of cumulative viral RNA released into the sewer shed is going to be governed by this equation, where alpha is the fecal load per individual, delta is the viral shedding per gram of stool, and eta is the losses in the wastewater due to degradation. And that's where that half-life sort of method comes in. All right. So we're going to validate the model. The wastewater data is daily, and our equation for viral RNA is cumulative. The objective function to be minimized is going to be given by the sum squared error. You'll notice that we're taking the log of both data sets before we pass it into the square and then sum it. And this is just to ensure some numerical stability here. So how did we do? Well, the answer is pretty good. The wastewater data is shown in orange and the model is shown in blue. So this left panel A is showing the total viral load in the sewer shed for any given day. And we fit to the first part of the data from October to end of December, and then we predict from end of December to January. And you can see that our viral curve matches what's happening in the sewer shed. Now, what's very important here is in panel B, where we compare the reported cases to our estimated cases. So the reported cases are shown in orange and our estimate is shown in blue. And what's important is that you'll see our model predicts approximately 10 times more cases at the peak than what was reported. And this makes sense if we think about the lack of tests that will occur, particularly during this time period, and that occurring at the peak when more people are sick, so more people need a test. You'll see that there's not a huge difference in the beginning of the wave in October, and that's again because not as many people were taking a test. So there wasn't a surge in demand here. We also see that the predicted peak of the wave is about 16 days before the reported cases, give or take. So in our closing remarks, the peak of infections was about 16 days earlier than clinical case reports, and the infections did peak about 10 times higher than reported, and that's in line with previous studies, going from 6.4 to 15 times higher than reported, depending on the time period you look at and depending on where you look. So hopefully what I've convinced you of is that this wastewater-based surveillance is a powerful tool for community surveillance. It's better than our clinical case data. And what we can do is use our data fitting to make better forecasts for the community. And it's not just limited to COVID. We are currently trying to leverage this for influenza and norovirus, but it's also been used in polio, for example. We can also connect this model, or wastewater data can be connected to relatively simple models with parameters that we can actually recover. And again, you may look at this and say, hey, what about the travel time? What about you assume that everyone has the same number of contacts, and that's all fair game, but this is looking for an average person in the community. Given it's 2024 and we've been in this for a while, there are some extensions here that would be very important. So there's multiple strains that can be accounted for. As we know, COVID has many, many variants, and that complicates the dynamics significantly in very interesting ways. Wastewater is also powerful because we can actually monitor variants much earlier, and that's something we're currently working on, is predicting what variants will win, so to speak, and become the next dominant variant. You can also include population structure. So some people look at schools versus towns versus a neighborhood versus, you know, kind of looking at these different patches for city versus rural. We can also look more in depth into viral decay and also vaccines and how they change the dynamics here with prior immunity, even if it's not from a vaccination. And we do have some work here on the multiple strains where we did a time delay or a delayed differential equation model and fit it to some data. And we did not a bad job, but we did find similar results in that the number of infections is probably higher than what is reported, especially now that there is pandemic fatigue taking over. I would like to say thank you to AWM Pittsburgh and Farjana for inviting me. This is the team that I work with. They are awesome, and I'm very, very grateful for all of their support and insights. And I would like to open up to the floor to any questions.
Thank you so much for the talk.